What's up, peoples? It is assumed that you watched that short 3 or 4 minute video on the Doppler effect. You've all heard the Doppler effect before, and they do a good job of showing what it sounds like when a car goes by blowing its horn, or a fast car goes by, or a plane, or any of that, but they do a really nice job with the animation. So if you have not watched that video, please watch the video. But basically, what you saw was a source of a sound making waves, so rippling out like that. But if the if the source starts to move, the wave fronts get bunched up on one end, and then they get farther away on the other end. Best I can do. Maybe one more. Okay, so here's that source of the sound approaching you. There's you. You can see here that while it's getting closer or approaching you, however you want to say it, getting closer or approaching, doesn't matter, the wavelengths are going down. And remember that velocity is frequency times wavelength, and the velocity of the wave is constant. So that means frequency and wavelength are inversely related. So if the wavelength is going down, our frequency is higher. On the other side, as it's moving away from you, so moving away or getting farther, however you want to say it, the wavelengths here are much bigger. So the wavelength has increased, which means the frequency decreases. That's why something sounds lower after it's passed you. If you have not heard an ice cream truck go by, it sounds all friendly as it approaches, and after it passes, the pitch drops, the frequency drops, because the wavelengths are farther apart, and it sounds evil. And then there's the moment it passes you. At this moment, the frequency is unchanged. It's the actual frequency of the source. If you were to graph this in some way, it would look something like this, where this is your frequency. And as it approaches you, it's got a nice high frequency, then it passes you and it drops, and then it goes to a low frequency. So this is when it's approaching, it's a higher frequency. The moment it passes you, that's when you hear the exact frequency, and this is moving away. So you hear like a wow. That was horrible, but I did it anyway. All right, so that's the conceptual, which I think you probably got out of the video better than I did here. The mathematical, oh boy. There are many Doppler equations. Your physics book actually has 4, which is ridiculous. But it looks something like this. It's the Doppler equation. It's not a big deal. It's how you use it that's important. So there's no way we would be deriving this from an activity. And there's other versions of this equation as well. This is the one we are going with, but you need to understand what each variable is. So FD is the frequency detected. That's what you hear, the detected frequency. Fs is the frequency of the source. The source is the source of the sound. So the actual frequency of the source versus what you hear in your ear. V is the speed of the wave in the medium, which will usually be given to you in the problem. And if it's a sound wave traveling through air, it'll probably be 343 meters per second, because that's about standard. Vd is the velocity of the detector. How fast is the detector moving? Vs is the velocity of the source. How fast is the source moving? So the reason we're going over each one of these is that you need to know what each variable stands for. Otherwise, the expression is useless. And in this case, we need to do a sample problem because there is a small problem-solving strategy that you need to apply. Otherwise, this equation doesn't work properly. So let's do a sample problem together. So for this example, let's say there's two cars moving in opposite directions. It is highly recommended that you draw pictures of the scenario, like super highly. It doesn't take long. Don't be detailed. Two cars moving opposite directions, one going east, one going west, and they are approaching each other. So this is how I'm going to draw that. Two cars. Fancy drawings. The one going east is the source of our sound, and the one going west is the detector. So I'm going to put an arrow the direction they're moving. And let's say that the problem states that the frequency of the source, it's blaring its horn, is 600 hertz. So two cars approaching each other. The source is moving to the right, and it's beeping its horn. We need to give these things some velocities. So we'll say the source is moving to the right at 20 meters per second, and the detector is moving left at 30 meters per second. Okay, before we can use the equation, we have our picture. We have to do one thing. This is the key to using the equation. Every year, there are people that just don't hear what I say, make up their own thing. I don't know what they do. It's really simple. The positive direction is the arrow from source to detector. Arrow from source to the detector. What I mean by that, it's a weird detector. What I mean by that is draw an arrow from the source to the detector. That's it. That's all you got to do. Some people have some real issues with this. I don't know what that issue is. Draw an arrow from the letter S to the letter D. That's it. Whichever way it points is the positive direction. So in this case, right, because this arrow points right, is the positive direction, meaning that the detector is moving left or the negative direction. Once you've done that, it's just a matter of subbing numbers into an expression. We have F frequency detected, frequency source, 343 meters. Oops, sorry, not yet. V minus VD over V minus VS. Subbing our numbers in, what frequency would the detector hear? Well, sub in our numbers. We got 600 hertz for the source. We'll assume 343 meters per second as the speed of sound in air. The velocity of the detector is negative 30 meters per second because we've defined right as positive. So I'm going to write minus negative 30 meters per second all over 343 meters per second minus a positive 20 meters per second. That's going in the positive direction. Take your time and use your calculator properly, and you should get that the the frequency detected. Now remember, they're approaching each other, and you know you should hear a higher frequency, so it should be higher than 600. You get about 692.9 hertz. So we are definitely hearing something of a higher frequency. Another scenario. Let's say it's the moment the two cars pass each other. You got the source going east, you got the detector going west. There is no math that you need to do here. Conceptually, if it's higher as the frequency is higher as the object approaches you and lower after it passes you, there's a moment where it's the same frequency, and that's the moment they pass each other. You don't have to do any work. The frequency detected is 600 hertz. No work needed to be done. Let's do another scenario. Let's say these two cars have now passed each other. Now the detector is on the left here moving west, and the source is on the right here moving east. we'll say that the frequency of the source is still blaring its horn at 600 hertz. We will say that the detector is still moving left at 30 meters per second, or west, and the source is still moving to the east at 20 meters per second. Most important rule, you have to draw an arrow from the letter S to the letter D. That was supposed to be green. There's my arrow from the letter S to the letter D. That arrow points left. That means left is positive. So that means the detector is moving in the positive direction, but the source is not. The source is moving right, and we've said left is positive. I know it's weird, but that's how this equation works. After that, you are just subbing in numbers. Now they're getting away from each other, so we know we should hear a lower frequency. So let's check it out. You do frequency detected equals the frequency of the source, 600 hertz, times 343 meters per second, minus the velocity of the detector is now positive 30. You don't have to put the positive in there. I just kind of do it to make sure I've focused on whether or not it's positive or negative. And then it's 343 meters per second. And then this will be minus a negative 20 meters per second. And when you do this, you get the detected frequency is 517.4 hertz. So it's pretty much a simple substitute and solve. I cannot stress enough. Your only job, well, two jobs. Draw a picture to help visualize the scenario, and then draw an arrow from the source to the detector. That tells you the positive direction. I know I've repeated myself a million times about that, but some of you are going to say, oh, so if it's on the right. No, never said that. Never said that. Every year there's people that make up their own rules for this. I think I see a pattern where I'm seeing no, just no. Draw an arrow from the letter S to the letter D to define the positive direction. That is all you do. Do not do anything else. Do not try to find patterns. Don't say the one on the left is always the negative. The one on the right is always, that doesn't make any sense. Please trust me. Most people don't have any issues with this. The only issues they have are the math, which can sometimes be a little weird if you're solving for, say, the velocity of the source here, or one of the variables in the fraction. Then it gets a little bit weirder. So you just want to watch your order of operations. Other than that, don't make up your own rules. Draw an arrow from the letter S to the letter D to define the positive direction. Then label your velocities in your picture as positive or negative to help you, and then substitute and solve. The Doppler effect, it's kind of important. So other than that, I hope you're doing all right. And if you have any questions, again, please just send me an email and ask your question. Take a picture of your work if you don't want to stop by for office hours, and I'd be happy to help you. But don't hand in blank stuff. That's kind of lame. All right. You all take care of yourself. Hope you're doing well. Bye-bye.